Welcome to Boiler Outage Mastery. I am Rafael Sanchez, and this is Chapter 1, Introduction to Solid Fuel Boiler Systems. Before we get into inspection techniques, repair decisions, or startup protocols, we need to establish one foundational idea that shapes everything else in this course. A waste-to-energy boiler is not simply a steam generator. It is four systems operating simultaneously, and if you treat it as one system, you will consistently misdiagnose what you find during an outage.
Let me walk you through the four systems. First, the combustion machine. The grate, bed depth, air staging, and the variability of the fuel all govern combustion quality. Poor bed turnover, wrong grate speed, or incorrect air zoning does not just give you bad combustion. It directly creates reducing pockets in the lower furnace that accelerate chloride-driven attack on your water walls. That connection is critical. Second, the ash handling system. Bottom ash and fly ash must be continuously extracted. If you cannot evacuate the bottom ash fast enough, bed depth changes, primary air distribution changes, and your combustion profile changes. If fly ash is backing up in the gas path, your deposit loading on the superheater increases and your cleaning effectiveness drops. Third, the gas conditioning system. The SDA, baghouse, induced draft fan, and stack are not separate from boiler reliability. Draft instability that shows up on the control panel often traces back to a fouling problem upstream, an expansion joint leak, or a fan imbalance, not a controls problem. Fourth, pressure part reliability. Water walls, superheaters, economizers, and refractory all have to operate inside strict temperature and chemistry windows while accumulating damage every hour the unit runs. The field rule I want you to carry forward from this slide is this: a problem in one system always appears in another. A combustion problem in the lower furnace becomes a superheater distress event. An ash handling problem becomes a gas path chemistry problem. If you only look at where the damage is and not at what caused it, you will repair the symptom and repeat the failure. Now, let me walk you through the gas path from left to right, because understanding this sequence is the foundation of disciplined outage scope development. Refuse enters through the feed hopper and lands on the Martin reverse-acting reciprocating grate. The grate transports the waste, agitates the bed, and governs primary air distribution across multiple zones. What happens on the grate directly determines what the lower furnace sees. Fuel variability, bed depth, and air distribution all change the gas composition that contacts your water wall tubes. From the grate, combustion gases rise through the lower radiant furnace. This is the harshest environment in the boiler. Flue gas temperatures commonly run between 1,000 and 1,800 degrees Celsius. Your tube metal temperatures are typically in the 350 to 500 degree range, precisely where chloride-driven active oxidation is most aggressive. I want you to remember that temperature window because we will come back to it repeatedly throughout this course. The gases then pass through the furnace arch and nose. This geometry controls gas residence time, mixing, ash trajectory, and the temperature distribution into the superheater region. Excess slag or refractory distress at the nose does not stay local. It changes temperature uniformity and particle loading across the entire downstream gas path. From there, gases enter the platen and pendant superheaters, then the convective superheater banks, then the economizer. Each zone has a cooler temperature, different dominant mechanisms, and different inspection requirements. The economizer is cooler, but it is not benign. Fly ash erosion, flow-accelerated corrosion at elbows, and acid dew point corrosion during transients are all real risks there. Finally, the gases pass through the spray dryer absorber, the baghouse, the induced draft fan, and up the stack. Study this diagram carefully. Every outage scope decision you make should start here. By identifying which zone the damage is in, what mechanism governs that zone, and what the connection is to the zones upstream and downstream. This figure is one of the most important reference tools in the entire handbook. It maps the boiler into 3 risk bands, high, medium, and low, based on the combination of thermal load, chemical exposure, and damage mechanism severity. The orange zones are your high-risk areas. The lower furnace and grate area carry the highest risk because of the combination of metal chlorides, ash fusion, and reducing conditions. Your tube metal temperatures in this zone fall right in the 350 to 450 degree window where alkali chloride deposits can partially melt and contact corrosion accelerates sharply. The superheater area is also high risk, but for a different reason. Here it is the creep-corrosion interaction at elevated metal temperatures combined with aggressive deposit chemistry. The blue zones are medium risk. The upper furnace water walls see deposit-forming chlorides and erosion, but at somewhat lower intensity than the lower furnace. The convection banks see fly ash erosion and differential fouling. The gray zones are lower risk when chemistry and flow are properly controlled. The economizer and back-end APC can be managed with routine inspection intervals if FAC, erosion lanes, and acid dew point corrosion are tracked and addressed. Here is the critical field lesson from this diagram. Do not apply the same inspection intensity to every zone. Your UT grid density, your replication sampling, your deposit chemistry sampling, all of that should be weighted toward the orange zones first, then the blue zones, then the gray zones. And when you find damage in a lower risk zone that looks like it belongs in a higher risk zone, that is a signal that something has changed: fuel chemistry, combustion quality, or flow distribution. That change is worth finding and fixing, not just repairing the damage and moving on. This table is your zone-by-zone reference for outage scope development. Let me walk through each row because the numbers here carry real engineering meaning. Starting with the lower radiant furnace, flue gas temperatures of 1,000 to 1,800 degrees Celsius, tube metal temperatures of 350 to 500 degrees. That tube metal range is exactly where the ZnCl-2KCl eutectic mixtures found in municipal solid waste ash are most likely to exist in a partially molten state. And molten salt contact with your tube surface is what drives the most aggressive corrosion rates in the entire boiler. Your scope here must go beyond thickness restoration. It has to address the mechanism, the furnace arch and nose, slightly cooler flue gas but still very heavy slag accumulation, and refractory degradation. The scope here is almost always refractory driven. If the refractory at the nose is failing, it changes the gas trajectory into the superheater and can create localized overheating in areas you would not normally suspect. The platen and pendant superheaters, tube metal temperatures of 480 to 650 degrees. This is where creep and external corrosion interact. You cannot separate them. A tube insulated by a heavy deposit runs hotter than your operating data suggests, and that extra temperature is accumulating creep damage you cannot see with a visual inspection. The convective superheater banks. The dominant issue here is ash bridging and differential fouling. One lane runs clean and hot, while the adjacent lane runs fouled and cool, producing uneven heat transfer and unpredictable tube metal temperatures. And the economizer. The coolest zone in the pressure part circuit, but still exposed to three distinct damage mechanisms: fly ash erosion, flow-accelerated corrosion at your elbows and return bends, and acid dew point corrosion during startup and shutdown transients. Every one of these rows should drive a specific inspection plan: mechanism first, scope second. I want to close this chapter with a concept that most outage teams overlook entirely. Ash streams are not just waste products, they are diagnostic evidence. Every time you open a boiler for an outage, you have access to two residue streams that tell you exactly what has been happening inside the machine since the last time it was open. Bottom ash and fly ash are both telling you something important. Bottom ash makes up 70 to 80% of the combined ash in a mass burn MSW unit. It tells you about bed behavior, burnout quality, and great mechanical performance. If you are seeing high unburned carbon in the bottom ash, you have a combustion problem. If you are seeing fused clinker in unusual locations, you have a local overtemperature or air distribution problem on the grate. Fly ash is the smaller fraction, but it is chemically more sensitive and more directly relevant to your pressure part corrosion environment. Fly ash carries the condensed alkali chlorides, the zinc and lead compounds, and the sulfate species that deposit on your superheater and water wall surfaces and drive the mechanisms we will discuss in detail in the next chapter. When you sample fly ash from the superheater hoppers and the economizer hoppers, you are reading the corrosion environment that your pressure parts have been exposed to since the last outage. The practical implication for your outage planning is this: before you finalize your inspection scope, review the ash chemistry data from the previous operating period. If the chloride loading in the fly ash has increased, your superheater is in a more aggressive environment than it was last cycle. If heavy metals are elevated, your eutectic temperature window has shifted. That information should change where you look and how aggressively you look. Ash is evidence. Use it.
Let me close this chapter with the 5 things I want you to take away and apply on your next outage. Point 1. WTE boilers are four coupled systems. Problems in one appear in another. Combustion, ash handling, gas conditioning, and pressure part reliability all interact. A combustion problem in the lower furnace becomes a superheater distress event. Point 2. Each zone has its own mechanism, inspection basis, and outage scope. Do not apply a single inspection standard to the whole boiler. Zone context determines the correct outage response. Point 3. The lower furnace 350-500 degrees Celsius tube metal window is your highest risk zone. This temperature range coincides precisely with the molten eutectic window for ZnCl2 codeposits, the most aggressive active oxidation conditions in the boiler. Point 4. Ash streams are diagnostic evidence, not just waste. Bottom ash tells you about bed behavior and grate performance. Fly ash tells you about the corrosion chemistry your pressure parts have been exposed to since the last outage. Point 5. Mechanism first, scope second, always. The central outage error is treating all damage as generic wear. Reliable outage scope starts with identifying the mechanism, not the appearance. Those are your 5 key takeaways for this chapter. In the next chapter, we will build on these foundations and go deeper into the next critical area of boiler outage mastery. I am Rafael Sanchez, and I will see you in the next lesson.